FA2 further maths, discrete random variables. So we're going to just pick up the last part of discrete random variables from what you started last year. And we've got a discrete random variable here. So you can tell it's discrete because it's got individual discrete values. The x values can either reach a value of 1, 2, 3, 5 or 8. So they could be ages, it could be numbers on a dice, it could be absolutely anything you like as long as they're discrete values. The probabilities of those happening are given to you there. And what I'd like you to calculate is the expected value of 4 lots of my value cubed. Right, so we looked at some of this last year when we started doing variance, for example, and we needed to find the expected value of x squared. And what we did is we took each of the values, we wanted to work out 4x cubed, so we took each of those values and we put them into this formula. So there we go, 1 cubed times 4, 2 lots of cubed times 4, 3 cubed times 4, and so on. Okay. Now the probabilities of these happening is not going to change. So it's important to notice that the probabilities are not affected by us doing whatever the value is cubed times by 4. That only affects the x values. So the probabilities are exactly the same. Now once we've got these two pieces of data, we can work out the expected value the same way as we did last year. We just do the probability multiplied by whatever the discrete variable was. So 0.1 times by 4, 0.32 times 32, 0.35 times 108, and so on. 0.2 times 500, 0.03 times by 2048. So that is what our expected value is. So there's those numbers I just reeled off, and 2048 times 0.03. Once you've done that, number crunch in your calculator gets you an expected value of 209.9. Okay, which makes sense. Just a quick look at the table. It puts it into about this region just here, which sort of makes sense because it goes right up to 2000. Right, so just in your notebooks, under discrete random variables, so a discrete random variable x has a function applied to it, whatever that function is. So there's lots of different functions that it could do to it. The expected value of that function is just the function itself applied to each of the individual values. Okay, so each of the individual values has the function applied to it. So let's say your function was something like times by 9. Your values independently might be the numbers on a six-sided dice. So when you're applying that function to each of the x values, you would do 9 times 1, 9 times 2, 9 times 3, 9 times 4, 9 times 5, and 9 times 6, because that would be the values on the sides of a dice. The probability is exactly the same. That doesn't change. That's the same whether it's the x value or whether it's the function applied to the x value. It also follows that variance does exactly the same, because variance, as you know, is the expected value squared, take away the expected value squared. Okay, so the expected value with each of the individual parts squared, added up, take away the expected value that you calculated a minute ago, squared. Okay, right, so look at one of these together. Notice that I've put the probability distribution in a different way rather than a table format. If it helps you straight away, what you could do is you could convert that to a table. You could do that quite easily. Put the table in 1, 2, 3, 4, 5, and the probabilities would be 1 over 14, 2 over 14, 3 over 14, 4 over 14, and this one would be 10 over 35. Okay, so you could very easily change this into a table format, and as soon as you change it into a table format, these two questions will be a lot easier. Okay, so let's look at the expected value. Here's the function. So instead of 1, 2, 3, 4, 5, I'm going to be doing 2 times 1 to the 5, 2 times 2 to the 5, 2 times 3 to the 5, and so on. So there's those parts. The probabilities do not change. So even though you're putting it in the function, it's still 1 over 14. If you try putting these numbers in, what you'll find is your probabilities will be too big. Remember, your probability always has to add up to 1. So 2484.3 will be the expected value I would get if I use the function 2x to the power 5 with those probabilities. Variance a little bit tougher because you've got a bit more calculations. I wouldn't say it's hard, but unfortunately it's more likely to make silly mistakes. So let's go through it. So we've got 5 over x cubed. Remembering it's only the 1, 2, 3, 4, 5 that gets affected by it. So we've got 5 over 1 cubed, 5 over 2 cubed, 5 over 3 cubed, 5 over 4 cubed, 5 over 5 cubed, and that allows me to work out the expected value, first of all. I know that's not what it's asked for, but you need the expected value because you're going to square it. So the first thing I'm going to do is just work out the expected value, and the expected value is about 0.5199. Notice I'm keeping it to 4 significant figures, so I don't make a rounding error. What about the expected value of 5 over x cubed squared? So that's the first part. So this is a new function in here. So what would I do? I would go to each of these bits, 1, 2, 3, 4, 5, and I would put it in there. And so I can work out each part individually. Notice I've changed it to 25 over x to the 6, because that's the same as that. And so therefore I'll just put those in. It wouldn't have mattered if you'd done 5 over 1 cubed squared and so on. It's exactly the same. Notice the probabilities, 1 over 14, 1 over 14, 2 over 14, 2 over 14, are exactly the same, even though the function is very, very different. Okay, so what have I got? Well, I've got the expected value of the function squared, and I've just got the expected value of the original function. So what I can do now, as the answer to that bit, I can work out the variance. So that's the expected value of the function squared, so that's there, plus the expected value originally squared. So there we go, put those two numbers in and got an answer out of 1.581. What I'd like to do now is if you just turn to page 10 in your books, have a go at the questions you couldn't do last year on exercise 1B, and that's just questions 2, 7 and 8.